Okay, this lecture deals with the product and quotient rules. These will give us more power to work with derivatives. Let's start with the product rule. That's the derivative of a product of two functions. So what is the derivative of the function f of x times g of x? Now I'm going to use the x plus h definition of the derivative to get the limit as h goes to 0, f of x plus h times g of x plus h minus f of x times g of x all over h. There's a pretty interesting trick that's involved here, and I've used it before when I was proving one of the limits. I'll show you what it is. I'm going to sneak a term in between the top two terms in the numerator. So I'm going to slip in here a minus f of x times g of x plus h plus f of x times g of x plus h minus f of x times g of x. And that stuff is all over h. Now what I'm going to do is break this up into two fractions, both of which will be over h. So I'll have the limit as h goes to 0, f of x plus h times g of x plus h minus f of x g of x plus h all over h plus the limit as h goes to 0, f of x g of x plus h minus f of x times g of x. All of that is over h. Now what I'm going to do in the first two terms is I'm going to, this g of x plus h here, I am going to factor it out of the numerator. So this equals the limit as h goes to 0, f of x plus h minus f of x all over h times g of x plus h plus the limit as h goes to 0. This time you'll see the common term that I have is f of x. So I'm going to factor that f of x out. So I have f of x times the quantity g of x minus h, g of x plus h minus g of x all over h. Now according to all those rules that we used, I'm going to get the limit. The limit as h goes to 0, f of x plus h minus f of x divided by h times the limit as h goes to 0, g of x plus h plus, now here the limit as h goes to 0 f of x, since there's no h in this quantity here, the limit does not affect it. It just comes to be f of x. So that'll be times the limit as h goes to 0, g of x plus h minus g of x all over h. And let's go ahead and put in the limits that we know. If we're assuming that both f of x and g of x are differentiable, it means I can take their derivatives, then this part right here is simply f prime of x. Now I still have to deal with the limit as h goes to 0, g of x plus h. Then I have plus f of x. And this part here, let me see if I can slide this in, is g prime of x. Okay. Now, something that I will prove in a second, not a second, after I do some examples. But it turns out that if a function is differentiable, then it is also continuous. So what I'm going to end up getting is that you can allow h to go to 0 inside of here, and you'll end up with g of x plus 0 plus f of x times g prime of x. So of course the g of x plus 0 is simply g of x. So the formula I have, d over dx, f of x times g of x equals f prime of x times g of x plus f of x times g prime of x. And that there is the product rule. Let me do a few examples to illustrate its purpose. Let's see, as an example, what is the derivative of 3x to the 4th times the square root of x? Well, according to the rules that we have, I need to take the derivative of 3x to the 4th, but I leave radical x alone. Then I leave 3x to the 4th alone and take the derivative of radical x. Well, this first piece, the 3x to the 4th, is really just a power rule problem. You take that 4 down front to get 12x to the 3rd, radical x, plus 3x to the 4th. The second piece, we did the derivative of radical x, and it turned out to be 1 over 2 radical x. And there's no need to simplify any of these things. You can leave them like that. That's fine. In fact, when I go about grading your work, it's easier if you just leave it in that format. I'm able to see it. The only reason you need to simplify is if you plan on using your work for more work after that, if you plan on using it later for something that is related to that work. Let's try another one. This time, I'm just using a different variable to show you that you need them sometimes. Let's do e to the t times t to the 5th plus t squared plus 1. Hopefully you can see it's important that I'm matching the t here, the dt, the t and the t. That means I'm taking the derivative with respect to the variable t. So instead of an x, I just have a t. That's why you see a bunch of t's inside of the expression. So according to this is the derivative of e to the t, but you leave the second piece alone. T to the 5th plus t squared plus 1. Plus this time you leave the e to the t alone, and you take the derivative of t to the 5th plus t squared plus 1. The derivative of e to the t is the best one of all because it's just itself, e to the t, and it was attached to t to the 5th plus t squared plus 1 plus e to the t. Now on the second piece, use the power rule for each of the pieces. So the t to the 5th will become 5t to the 4th. T squared will become 2t, and the derivative of a constant is 0. So I just finished that one off. Like I said, don't bother simplifying. There is no need to do it. How about this one? D over dx of e to the 2x. What is the derivative of that? Well, what you could do is remember your rules for exponents. You can write this as e to the x plus x. And you can continue d over dx of e to the x times x. Remember, that's the rule of exponents there. You add the exponents together if they have the same bases, and you can break it up into a product. Now, I can take the derivative of the first e to the x while leaving the second one alone, and then I can take, or leave the first one alone and take the derivative of the second one. These, of course, are all very simple because the derivative of e to the x is e to the x. So I get e to the x times e to the x plus e to the x times e to the x. And so that equals e to the 2x plus e to the 2x. Oops, I don't know what that creature was. Equals 2e to the 2x. And you can use this to build on e2 powers. Like, for example, check this one out. D over dx e to the 3x equals d over dx times e to the 2x times e to the x. And now I can do the product rule on that. I'll have d over dx times e to the 2x while I leave the e to the x alone, plus e to the 2x times the derivative of e to the x. Well, as we just did the example, d over dx e to the 2x equals 2e to the 2x times e to the x plus e to the 2x times e to the x. And when I multiply the first part here, I end up with 2e to the 3x plus, and then this piece right here is e to the 3x, and I end up with 3e to the 3x. So that's a lot of things you can do with this stuff. If I go d over dx e to the 4x, I can rewrite it as d over dx e to the 3x times e to the x, and then do just like I did before, d over dx times e to the 3x while I leave e to the x alone, plus e to the 3x times d over dx e to the x. Now we just did the derivative of e to the 3x, that is 3e to the 3x times e to the x plus e to the 3x times e to the x. So you get 3e to the 4x plus e to the 4x, which, as you might have guessed, is 4e to the 4x. So you can keep doing this all day long. You'll eventually get to the point where you have d over dx e to the kx, where k is a natural number, is going to equal k e to the kx. And then if you want to use some induction, you show that the next step holds, just like in the problems I was doing. So what if I have k plus 1 times x? So that's d over dx e to the kx plus x, which equals d over dx e to the kx times e to the x. And then use the product rule, d over dx of e to the kx while I leave e to the x alone, plus e to the kx times the derivative of e to the x. And then, as we just went through the effort of assuming, I'm going to have, for the first piece, I'm going to have k e to the kx times ex plus e to the kx times e to the x. And then when I multiply these two together, I get k e to the kx plus x plus e to the kx plus x. So that equals k e to the k plus 1x plus e to the k plus 1 x equals k plus 1 times e to the k plus 1 x. So if you remember your induction efforts from college algebra, they come into use here. Now, I made a point before that I was allowed to change that h to 0 inside of the gx. The theorem goes like this. If f of x is differentiable at a, then f of x is continuous at a. So if we have a function that we can take the derivative of a, then I know it's going to be continuous at a. So the proof goes something like this. We want to prove, so let's say want to prove that the limit as x goes to a of f of x equals f of a. That's exactly the definition of continuity. And usually when we're dealing with continuity, we start looking at things like this. F of x minus f of a, but usually an absolute value. But I'm not going to do that right now. I'll show you why. This is going to equal f of x minus f of a all over x minus a times x minus a. Then I'm going to do this. F of x equals f of x minus f of a all over x minus a times x minus a plus f of a. So the little trick that I did here where I multiplied and divided by x minus a is because when we're dealing with the limit, we don't actually care what happens at a itself. But watch what happens here. I'm going to take the limit of both sides. The limit as x goes to a, f of x equals the limit as x goes to a of f of x minus f of a all over x minus a times x minus a plus f of a. And you can take the derivative, or not the derivative, the limit of each piece of this. Like this part right here is f prime of a. That's an alternate version of the derivative. The second piece, the x minus a, well, as x goes to a, that piece is going to be 0. And f of a has absolutely no h in it, so it is unaffected by the limit. X is going to a doesn't mean that a is involved in doing anything. X is the variable here. So since there's no x in the variable, no h, no nothing, that is just f of a itself. So we end up then, when you clean up everything, limit is not h goes to 0, but x goes to a. F of x equals f of a. So therefore, f is continuous at a. Now, the converse is not true. Like, you can have a function that's continuous, but it's not differentiable. So let's make a note of that. Note. The converse is not true. That is, there are functions which are continuous at a, but not differentiable at a. Why? Well, let me give you the example one of the examples that shows why it's not true. If you have a function, something like this, where it comes along, it's nice and smooth and all that, but all of a sudden that goes and has a sharp peak to it. Do you remember the derivative will not be defined at this peak? The reason why is because the slope of the tangent line from the left is quite different from the slope of the tangent line coming from the right. So when you compute the derivative, you'll get a different answer if you do the left-hand derivative versus doing the right-hand derivative. So I think we should put not true, if I can somehow make this important statement here. In math, I'm going to back up just a little bit. In math, when I say if f of x is differentiable, when I say if f of x is differentiable at a, I'm assuming that the function is differentiable at a. And because I'm making that assumption, I'm able to prove that f of x is continuous at a. I can't do the same thing here. I can't say that if the function is continuous at a, then it is differentiable at a. So there's a first and a second, or the assumption and the implication is the second piece. I cannot turn this around and say that the converse is true. Deductive reasoning, things of that nature. Well, anyways, let me go on. Let me go to the quotient rule. That looks like a W, and I didn't mean that. So we'll try to make it U-like. Quotient rule. Now, anytime I write these rules, please assume that each of the functions is differentiable. So I'm going to have f of x divided by g of x. What does that equal? Well, what I'm going to do is this. I'm going to let r of x, I saw this in a book and it's a much better way than I was planning on doing it, so I thought I might copy that method. Alright, now what I'm going to do is I'm going to multiply both sides by g of x. So I'm going to have f of x equals r of x times g of x. Now I'm going to take the derivative of both sides. So on the left side, that's easy enough. I get f prime of x. But the right side, I have to use the product rule. R prime of x. One of the reasons I like this method is because it harkens back to a rule we just dealt with. So according to that, that's r prime of x g of x plus r of x times g prime of x. Now the thing I want to find the derivative of back here is no different than the derivative of r of x, because r of x I set equal to f of x over g of x. That means that this guy right here is the one I want to solve for to get my formula. So the first thing I'll do is subtract r of x times g prime of x. Now, clearly, if g of x is in the denominator, we're assuming that wherever we're taking the derivative, g of x will not be 0. So I'm going to divide both sides by g of x. If you don't mind, I'm going to put my r prime back on the left. For some reason, most of us feel more comfortable with the thing we're trying to solve for being on the left side. So I have f prime of x minus r of x times g prime of x. All of that is divided by g of x. Now, if you recall, r of x was equal to f of x over g of x. And this is one of those times when your algebraic competency will be tested. If you're not good with fractions, you have trouble with them being divided, a fraction divided by fraction, you're in for quite a load in these selection of problems. I'm going to replace r of x with f of x divided by g of x. And don't forget, that's times g prime of x. And the entire thing is over g of x. Now in the numerator, I am going to get g of x as a common denominator. That means I need to write the first piece as f prime of x times g of x. And here's what I get. I get f prime of x times g of x minus f of x times g prime of x. And all of that is over g of x. But that whole thing is over another g of x. And this is where you might get a little frightened if you're algebraic phobic. You probably should think of this g of x as being g of x over 1. And that way I'll remember how to flip the thing. So I'll get f prime of x, g of x, minus f of x times g prime of x. All of that, what if it won't let me take it out? Did not. There it goes. All of that over g of x, the quantity squared. Because once you invert this thing, you'll get 1 times the numerator. The 1 will come up in the top and be multiplied towards the numerator. And the g of x would multiply towards the denominator. So let me go back over here. This thing is called the quotient rule. Well, because you're dealing with a fraction or a quotient. Let me do some examples with this one. Let's let y equal 4x e to the x all over x squared plus 1. So then dy over dx, remember the Leibniz notation, this is the same notation as f prime of x. I just happen to be using a y. So I'm going to be taking the derivative of the numerator, 4x e to the x, leaving the denominator alone temporarily, minus, then I'm going to leave the numerator alone, 4x e to the x, times the derivative of x squared plus 1. All of that is over the denominator squared. Now let me start taking derivatives. Now up here in the numerator, this piece right here, I'm going to put a dot between the 4x e to the x, because to do that, I need to use the product rule. So if you remember, I need to take the derivative of 4x first. That's 4 e to the x. And then 4x, take the derivative of e to the x next, which is e to the x. Of course, you leave the x squared plus 1 alone. Minus 4x e to the x. The derivative of the second piece is just the power and constant rule combined. I'm going to get 2x plus 0. Nothing to do in the denominator except rewrite it. X squared plus 1 squared. Once again, don't bother simplifying things. In fact, even if you leave that 0 right there, that's fine with me. I'm going to simplify just a little bit, but you're not required to. So I am going to leave all of this stuff alone. So I have 4 e to the x plus 4x e to the x. My x's are a little bit sloppy. Let's fix that. Times x squared plus 1 minus 4x e to the x times 2x. I think what I might do there, seems so hard not to do it. I'm going to change this 4x to an 8x squared. But I don't want to get carried away. I really don't want to do any more simplifying. I want to be done with it and just move on. So there you go. Let's do another example. How about the derivative, d over dx, of x to the negative n, where n is a natural number? Well, it's probably best to rewrite x over negative n as 1 over x to the n, because now I can use the quotient rule. The quotient rule says I take the derivative of the numerator first while leaving the denominator alone, minus I leave the numerator alone. Try to make my 1 so you wouldn't. And then take the derivative of the denominator. And that's all over the denominator squared. The derivative of 1 is 0. 0 times x to the n. Minus 1 times n, x to the n minus 1. We did that last time. All over x to the 2n. 0 times x to the n goes away. I end up with n x to the n minus 1 over x to the 2n. Now let me simplify a little bit here. I'm going to rewrite the numerator as n x to the n times x to the negative 1 all over x to the n times x to the n. The reason why I did that is so that you could see how the simplifying works. And then I'm going to take the x to the negative 1 down here, and I get n over x to the n plus 1. Or, what's even better, is n x to the negative n plus 1. So if you will, this is no different than the power rule. This is the power rule for negative exponents. So d over dx, x to the negative n, equals, come back for a second, I missed this minus sign. Let me put the minus sign here. The minus sign goes here, here, and here. So the derivative of x to the negative n equals negative n x to the negative n minus 1. So I'll call that the negative power rule. And I think one last example that I would like to run through is sort of a reminder of something we've already been doing, but I don't want you to forget one of the reasons we do these things. So compute, or determine, I like that word better, determine the equation. I shouldn't say the, because there's more than one way to write these things. How about determine an equation for the tangent line to y equals x squared minus 3 all over e to the 3x at x equal to 1. So remember, to get the equation of a tangent line, that's a line, we need a slope and I need a point. So let me get the point first. The x value is given, so it's 1 comma something. So y equals 1 squared minus 3 all over e to the 3 times 1. This looks to me like it's negative 2 over e cubed. So negative 2 over e cubed is the point. Now let's determine the equation of the tangent line by getting the slope. So to get the slope, I've got to take the derivative of y, dy over dx, equals, take the derivative of the numerator first, x squared minus 3, leave the denominator alone, minus, leave the numerator alone, and then take the derivative of the denominator. So we have the derivative of x squared minus 3 times e to the 3x minus x squared minus 3 times the derivative of e to the 3x, and I have e to the 3x e to the 3x squared. Okay. The derivative of x squared minus 3 is 2x, so I get 2x e to the 3x minus x squared minus 3 times 3e to the 3x. All of that is over e to the 6x. So now to get the slope, when x equals 1, I need the derivative's value at x equal to 1. This will give me my slope. Remember that notation? When I write this notation, this is the derivative evaluated at x equal to 1. So everywhere I see an x, I'm going to replace it with a 1. So I have 2 times 1, e to the 3 times 1, minus 1 squared minus 3 times 3e to the 3 times 1, all over e to the 6 times 1. So it looks like I have 2e cubed plus 6e cubed. Give me a second here to show you why that is the case. If you look right here, negative, inside these parentheses, I'm going to get a negative 2. So a negative 2 will be positive 2. But then when you multiply it by 3, you'll get positive 6. And this is all over e to the 6th. This equals 8e cubed over e to the 6th, which simplifies to 8 over e cubed. So I've got my point. Where was the point at again? That was 1 negative 2e cubed, negative 2 over e cubed. So my point was 1 negative 2 over e cubed, and my slope was 8 over e cubed. So, then the equation of the line looks like this. I have y minus y0 equals m times x minus x0. Let's plug in what I have. My m is 8 over e cubed. My x0 would be the point 1, would be the number 1. And then we have y minus negative 2 over e cubed. So that's the equation of the line. That's good enough for me. However, I want to check it. I just want to show you that it works. So what I'm going to do is this. The slope int form, it's not required, but I'm going to do it anyways. So I have y plus 2 over e cubed equals 8x over e cubed minus 8 over e cubed. Now if I add the 2 over e cubed to both sides, then I'll end up with a negative 10 over e cubed over there. So I have y equals 8x over e cubed minus 10 over e cubed. If that's the version you like, fine. What I want to do is check it on a graphing device. So let me go back to the actual function itself. X squared minus 3 over 3x. So I'm able to put that stuff into my graphing program. I'll insert a function. So you type it practically, you get, except x squared, it's got to be x caret 2. So I get x squared minus 3 divided by, to be on the safe side, I better do e to the, and I need 3x in parentheses as well. Now in the same graph, I want to graph the tangent line that I found. And I need to put it in this format, just like you're probably most comfortable with. I'm not sure why that's the most comfortable format. For me, I like this one because it shows the shifting up and to the right of the original function y equals mx. But whatever. Let's go ahead and throw that thing in the calculator for my second function. So I have 8x divided by e compute. Minus 10 divided by e cubed. Let's graph it. Better touch there, right, when x is equal to 1. Look at that. Let me zoom that in. In fact, let me grab it with my hand. Look at there. It's touching right there. And you can see it's touching just at that one point locally that is speaking. I can zoom in more and more and more just to show you how obvious it is. Right there. Connecting at 1. What was that point? Let me see. I can actually go through the effort and graph a point series. The x value was 1. And the y value, what was that? Was negative 2 over e cubed. It lets me put that stuff in that way. Negative 2 divided by e to the third. And as you can see, it throws that point right there. Right in the target where I thought it should be. So that makes me feel very good about if I got this problem correct or not. Next time we're going to do a bunch of stuff with the trig functions. It should become a lot of fun.